everyone. Welcome to PHYTEC's very first webinar. We're so glad you could join us today. My name is Desiree Archuleta. I'm the marketing coordinator here at PHYTEC, and I've been with the company for 3 years. Today, we will be presenting 5 tips for designing an embedded system with PHYTEC, and our presenter is our very own hardware engineer, Johnathan Feuerstein. Before I introduce John, I'd like to quickly go over the agenda. So today, we will start with the technical talk and follow with a live Q&A. We encourage you to submit any questions that arise during any point in the presentation through the Q&A function on your screens. Now back to John, who actually made that tune you all heard just a minute ago himself. Okay, John has been at PHYTEC for 6 years and has done everything from schematic capture and verification to circuit design and test fixtures. He's designed one of our latest products, the PHYCore AM65X, and has tons of experience working on PHYTEC and custom carrier boards. So without further ado, I'll pass it off to John.
Awesome, thank you, Des. Welcome everyone, thank you for listening in. Today we're gonna be discussing some useful concepts you can incorporate into your embedded design process. It's gonna be more focused on the hardware perspective, but if you're not a hardware engineer, that's okay. I think everyone will be able to take something away from our discussion today. So creating a design from scratch is challenging, involves reading through tons of documentation, designing complex circuits, sourcing and purchasing components, manufacturing or finding a manufacturing partner, debugging and testing your design, and on and on. And PHYTEC sees this challenge as an opportunity to save our customers time and money and support them along the way. And so to do that, we design and manufacture embedded system on modules, or SOMs. By using a PHYTEC SOM, you can eliminate that additional overhead of reading through the documentation, doing the designing, the manufacturing, the testing, and successfully integrating a CPU, DDR memory, flash memory, power management, and so on into your embedded system. Our off-the-shelf solutions have already gone through those development and verification processes, and they're ready to plug into your application. So for an example, I have a SOM here to show you that's based on the NXP IMX8M Mini. This is a BGA low-profile SOM that can solder down to a carrier board, incorporates the silicon from NXP, power management, flash memory, DDR, and all those things that I just touched on a moment ago. So today, the tips I'll be sharing will come from this experience of integrating embedded systems, and the list of things we talk about could be endless. There's so much to learn in the world of embedded systems and improve on, but I try to pick out some of the basics that are helpful to keep in mind, and we're gonna talk about these concepts when designing a carrier board around a PHYTEC SOM and show what PHYTEC can offer as a partner throughout this process. So let's get into it. Tip number 1, component selection. Be intentional when selecting each component. So when you drop a part into your schematic, you should ask yourself why you selected that one in particular and build a habit of being mindful and don't just blindly copy and paste. This is one of the first things I learned early on at PHYTEC as an engineer. Before I knew and had confidence in circuits in my design, I'd just pull in parts, copy reference designs, and just kind of take their word for it. But eventually I realized that can create issues. You might pick parts that aren't appropriate for your specific application, don't meet the requirements that you hope for. And this can create problems when it comes time to generate the bill of materials. So some of the things to think about when you're selecting components: cost, what's your budget, what volume are you going to be producing. You might find a part that's great, oh, these specs are awesome, they're going to fit just right in. But then you look at the price and whoa, it's very expensive and you're trying to use this 10 times in your design, and you're going to be building thousands of units a year. That's going to start to quickly add up. So be mindful of that and watch out. Availability, what are the lead times of those parts? Okay, cost is good, I'm ready to go. But I look and now there's only one supplier for this part. I don't see any stock and it's gonna take 20 weeks to get this part. That might not work out for your deadline or your timeline if it's really time sensitive. And you wanna make sure you future-proof yourself to make sure you'll be able to buy these parts for the product life cycle. And speaking of life cycle status is also important to pay attention to. Always monitor because things can change quickly. And what I mean by life cycle status, we're talking about things like EOL, or end of life. And that's when a part is no longer sold by a manufacturer. And at that point, you're gonna have to design in a new part and replace it. So ideally, you think about this ahead of time and you can future-proof with a package that allows for drop-in replacements so that you don't have to spin a whole new PCB. So for example, we were recently working on design and we were doing a weekly status check of components. And we found a connector which had 5 years of expected availability, and all of a sudden it had a PCN. Luckily, we were able to drop in a replacement before the prototype build, and that avoided the constant revisions and changes. that would have happened throughout the product if we had left that old connector in there. So to get into a specific example, kind of show you how this works in action, we recommend double checking your BOMs. This is really critical. So in this example, perhaps your design uses this boot configuration circuit. Somewhere else, there's a NOR flash part. And you see here that we're using this 10K resistor throughout. So during schematic capture, I'm pulling these in. Maybe I take a, I go grab some lunch. I come back and I start working on the NOR flash after I'd already done the boot circuit. And then without thinking, I just pull in some random 10K resistors and not really thinking about what I used before. That seems fine, right? It's just 10K resistor. At the schematic level, they're the same, it's fine. But when we take a closer look at the generated BOM, that's where you can see the sort of problems you might run into. So here's an example of a BOM you might run into with this design from the previous slide. Here you see all these different 10K resistors. Note the differences in your tolerances, 5%, 1%, 0.1%, and your temperature coefficients. Of course, the pricing will be different here. So if you're not paying attention, you might throw in something that's really expensive when you could have just used another part you were already using that was more reasonable. And it also creates more opportunities for PCN and life cycle issues to come up, right? If you have 5 different parts from 5 different manufacturers, one of those might go EOL, whereas if you just had one part from one manufacturer that you vetted out ahead of time, it's going to be a lot easier to manage and less overhead for you in the long run. So it's a good idea to do these design reviews after finishing your schematic and before moving on to layout, and sort your BOM and look for these parts that you could consolidate. Another important factor too to keep in mind is when you go to production and you have pick and place machines that use different part reels. Here I have 5 or 6 different 10K resistors maybe, and that's going to lead to 5 or 6 different component reels that are going to be loaded into this machine. As your BOM grows with your schematic, as you get to completion, that can start to add up quickly, and that might create delays through your pick and place machine line. You might have to go through multiple times, which is just going to add more time and more cost. So if you simplify this, reduce the number of reels, and save yourself some time. All right, moving on to tip number 2. Use available supplier resources to save time. Probably see a theme here, trying to save that time, trying to save money. There's lots of resources out there that can help you accomplish this. So manufacturers often provide different tools. These include power design tools, timing spreadsheets, perhaps for memory, RF tuning calculators, among many others. In addition to that, in their data sheets and their documentation, they'll often give you specific recommendations for associated components, such as bypass capacitors and strapping resistors. These are useful because you can use something that's been tested and recommended from the manufacturer themselves, rather than just doing that work manually, maybe using your gut or experience from the past to try to pick these values, maybe even do manual calculations. So just follow those recommendations and try to use those when appropriate. And then finally, follow layout guidelines. These are very helpful, often critical for placing parts properly to ensure that they function as you expect, to reduce emissions, and make sure you're optimizing your power. This picture here that we have is a screenshot from our design and guide for one of our SOMs. So here we're showing the trace lengths of this high-speed differential interface on our SOM. And that allows our customers to take that information and design their traces appropriately on their carrier board, rather than just doing that from a guess or from scratch. So utilize these resources, explore and see what's out there. So to kind of give you some more perspective on this, manual calculation, right? It's time consuming, it's error prone. So let's pull out our paper and our pencils, get some paper, crunch these numbers. Maybe you've seen some of these equations, right? They pop up in data sheets. I know I've seen some of these trying to calculate parts for design. Some are easy, some are more complicated than others. This one here is from our director of engineering. He said he used this in a design about 9 years ago. I wouldn't want to mess with this or get into that. I'm sure a lot of you probably don't either. So rather than doing these manual calculations, taking all this time and rewriting and recalculating depending on parts changing from your component selection, try to use tools that will give you recommendations to bypass this. So an example of that would be this nice power design tool from TI. You can enter your input and your output voltage and the rest of your specification. You can put in your priorities for your design, such as low cost, or if you want more efficient, if you're worried about footprint. And then rather than doing a lot of these calculations on your own, it'll spit out a bunch of part recommendations. It'll give you entire circuits based around those different regulators and parts. It'll give you part numbers. It'll give you simulation results. And these things are very useful and can save you a lot of headache and trouble. So check out manufacturer websites, spend some time exploring. there might be resources that surprise you and cut down development time significantly. All right, moving on to tip number 3, start thinking about layout during schematic capture. Think about things like what physical size are you targeting for the design? Are all your connectors and your components going to fit within those dimensions? You might need to make compromises based on the physical limits. This may seem kind of obvious, maybe simple, but if you're not careful, if you're not working with your team, you're not working with your product team, those that are working on your specification, interfacing with customers to see what's important to them, it can be easy to just kind of stick to the schematic, just work on your circuits, get it out there, try to get it done within your deadline without thinking about layout and the next phases that are coming afterwards. So take care when you're selecting your components, like I mentioned before, because that can also impact the layout. So give some examples of those and how your schematic implementation can impact your physical signal transmission. You want to watch out for your connections, especially for your high speed and your sensitive signals. So here on the left, we have a screenshot of a filter that's on some CAN signals. In this example, I decided I wanted to add bypass resistors around this. This allowed me to test that filter value. Maybe I can drop in other values depending on my testing, or maybe I might run into issues and I want to have a way to fall back on this bypass resistor so I can not be blocked during my testing and get this interface functional. Seems like a good idea, simple enough, not a big deal to add these resistors in the schematic. But as you see on the right, when we get to layout, and the layouter places these resistors, you can see those highlighted extra traces that are branching away from the main signal path. These are stubs, and those create impedance changes on the signal trace, and those can possibly cause reflections, which lead to signal integrity problems. In the case of CAN here, it's a relatively slow interface. It's not much of a concern, but you can see how easily it is to add pull resistors to other components like this. You can easily add those to your high-speed interfaces, things that are more sensitive. And if the layouter is not careful, they could place these even further away, creating larger branches and even more problems. So in cases like that, maybe it's better to pass on these bypass resistors and just be confident in my design, spend more time making sure that it's going to work as expected and avoid that risk. One more example here for layout. Another helpful thing to keep in mind is pay attention to the available package options. So oftentimes components will allow you to order them in different packages, and it's nice to select components that improve signal routing when appropriate. And so this example I'll use to expand on what I mean by that. So on the left, you see D13 highlighted. This allows for what we call pass-through routing. The signal traces are routed straight through the pins, and there's minimal impact on the spacing between the differential pair signals. Alternatively, on the right, you see D19. That's not set up for pass-through routing. It's just kind of a standard package. The differential pair signals are separated to connect to the pins, and this breaks the spacing requirements for the differential pair. That could potentially have a negative impact on your signal integrity. In this case, it looks like a pretty small break in the spacing, but you can see how the more parts you add throughout the schematic and the packages that you choose will really impact how what the layouter can do, and may have negative impacts later down the line. So watch out for these, keep it in mind, and try to make life easy for your layout team. All right, tip number 4, again with layout, prioritize placement and think in 3D. So component placement is a critical step at the start of your layout, and that can really help you avoid future roadblocks. Placing sensitive components first is really key, and that sounds another thing that sounds obvious, but it's easy to look over. So take care of your difficult and sensitive interfaces while there's room. You don't want to try placing those later when you're limited with space, when you've placed all these generic components and maybe your passives and your bypass caps. So just watch out for that and place those first, make things easier for yourself. The mechanical fit, avoid mating issues by looking at physical cable connections. And what I mean by that is it's easy enough to place some connectors on a board and maybe it looks like, oh great, these fit along the edge. But when it comes time to actually plug in peripherals, plug in a cable, you might not be able to plug two next to each other because the cables are wider than the connectors themselves. Something like this is hard to visualize unless you've run into that problem before or have someone that has experience with that. So watch out for it. Think about the 3D while you're working in your 2D schematic and layout. And that brings me to mechanical collisions, which is related. Again, watch out for 3D collisions that don't show up. And to show you an example of that on this next slide, here we have a 3D model of a board. I don't know if you can see here, but there's a part that's highlighted that shows this connector is conflicting with this edge of the PCB. And we actually have a real life picture of that. When it went to production team tried to solder it down. Oh, this connector's popped up at an angle and it's not flush with the edge of the PCB. This could be a real problem if you're trying to fit this board into an enclosure. It's not flush with the hole that you have cut out for this connector. And maybe if it was even worse, the production team might not even be able to solder it down at all. So PHYTEC is improving its 3D capabilities, and we're generating 3D models to perform a 3D review check to help avoid issues like this before reaching production. So we can catch these conflicts, we can adjust the layout appropriately and make sure the footprint meets our expectations. All right, moving on to tip number 5. After layout's done, we want to go to production tests. But we want to make sure that we're thinking about tests during design as well. So simplify production and automate tests. It's very helpful to consider how you're going to test your system after and while you're designing it. And there are 2 kinds of design for tests: testing and verifying your design, and testing units as they are built in production. While additional circuitry increases costs and takes up space, the benefits can often outweigh these impacts. And so today we're just going to focus on the designing for production tests specifically. So when your design's complete, hopefully you're going to be producing this in volume for many years, and you want to think about who is going to be testing your design. Are you using a third-party manufacturing facility, or are you going to do this yourself? If it's all manual, then things can start to really add up and become more overhead than you may have intended. So you could set up a manual test that involves the user connecting cables, powering up the unit, running commands, probing points around the board, writing down results. Or alternatively, you could use a test fixture to automate the test. So this example I have here in the pictures is a clamping fixture for the PCBA you see. And you can see in the picture on the right that the carrier board has a PHYTEC SOM mounted on it, on the other side there. So as this fixture is closed down and clamped, test probes from the bottom will come up and make contact with the board, and that allows for an automatic test to run. This requires thought ahead of time, though, to design in with a test fixture in mind, such as adding test points for those probes to contact. But this is less prone to error and significantly reduces overall test time. So it might be hard to imagine when exactly you should decide to do automatic versus manual. Production test automation can be expensive. The upfront costs are definitely more significant. So here we kind of have an estimate based on some of our own experiences with test fixtures and manual tests. So our cost estimate on the left for our manual and on the right for the automatic. Definitely significant at first, right? Maybe that's daunting and kind of deters you from a manual test, but when you take a closer look at the test cost per unit, that's when things really start to change and lean more towards in favor of the automatic solution. Right, on the manual here, we estimate about 15 minutes per unit. Of course, that'll vary, could be more. In our automatic test, by running everything in a script without a user using the tests themselves, we get the time down to about 3 minutes per unit on average. So kind of show that visually, here's a graph that's showing the number of units produced and what the cost is as those units increase. And so when is the development worth it? And that's about at the break-even quantity, right? So here it's about 3,200 units in our example, but we also have a table here to show you about the number of years it takes for that cost to meet up, depending on the amount of units you're producing. So PHYTEC recommends about around the 500 to 750 units a year range is when the benefits significantly start outweighing the costs, and you would seriously want to consider using an automatic solution. But even at low volume, it can still be a good idea to design with an automatic test in mind in case the product becomes more successful than anticipated. And it's also good just to build those habits in case you reuse circuits or designs for future products. But whichever path you take, at least take time to consider these options. Test time can add up, and a design that is difficult to test can end up creating unnecessary overhead. All right, and those are my tips. So just kind of a review to make sure we have these all covered. Component selection, be intentional when selecting each of your components. Pay attention to cost and life cycle status. Design resources, use your available supplier resources to save time. Don't rely on yourself and all the manual calculations when there's things that are already done out there for you. Layout considerations, start thinking about your layout during schematic capture. Don't wait until the schematic's done and then have a discussion with your layout team and have to revision and turn back and lose time in your development process. Component placement, prioritize placement, and think in 3D, not just 2D. And then finally, design for tests, simplify your production, and consider automating tests when appropriate. And just kind of talk about what PHYTEC's about, some of the things that we do. We offer those off-the-shelf SOMs that I mentioned before. These have already gone through design and verification. Really takes a lot of the overhead out. You don't have to design that from scratch on a chip-down design. and it can quickly plug into your application and get you going. Experience, 30+ years of design and manufacturing embedded electronics. We have a dedicated team of hardware, software layout engineers that are working on these schematic and layout designs. The shared expertise allows us to compromise efficiently and create these robust embedded systems. And we leverage that experience to debug our customer problems effectively, and we offer design assistance so that you can avoid these common pitfalls that we've talked about today. And then finally, PHYTEC manages our product change notifications and lifecycle status changes for components across all of our products. We take appropriate steps to work around these changes with minimal impact. We notify our customers accordingly. By deploying a PHYTEC SOM, you can rely on our products being in production for 15+ years. And kind of diving into more of the specific services we have reference development kits for all of our SOMs. These are carrier boards that you can use that have known good circuits that you can repurpose in your custom designs. It also allows your software development team to work in parallel with your hardware development so that we can get to market faster. Our quality support, consult with our engineers for design questions about pin muxing and other things. Schematic review, free checks for mistakes. It's always good to have a second set of eyes. Custom hardware design, if you don't even want to worry about designing your own carrier board, we also offer services to design carrier boards for you. And finally, manufacturing, we offer high mix, low volume in-house production capabilities to handle all your production needs. All right, thank you everyone for taking the time to join in and listen to our presentation. I'm going to hand it over to Des to wrap up and moderate our Q&A session.
All right, thanks, John. That was awesome. Let's jump right into the Q&A. We have some questions in here. All right. Are PHYTEC SOMs FCC/CE certified?
Yes, they are. So we use a third-party facility around here to bring our SOMs into the testing chamber and certify those and look for problems that we can resolve.
All right. Next question looks like a three-parter actually. So we have, will the tools be able to help with appropriate trace spacing? Is it advantageous to do multiple layers for routing? And if I use multiple layers, will I be able to tell if my clearances are still appropriate between layers?
Good question. Yeah, so here we're using Mentor graphics, and we set what we call layout constraints up, and it's where you can go in and you set the spacing that you want for your traces, and the tool will automatically check for those and make sure you're not, creating these problems. It is advantageous to do multiple layers. Depends on your board size. If you can afford a large board space, you can use less layers because that gives you more space on each layer for routing. But for our SOMs, we use more layers because that way we can reduce the size and still be able to bring all these signals out to the connectors. Hopefully that answers your question.
All right, next question. What schematic and layout tools does PHYTEC use?
Yeah, so we use, again, Mentor graphics. We use the schematic and layout tools from them and a nice suite. And that allows our teams to work together and quickly get to layout after the schematic is done and collaborate.
All right. Does PHYTEC make schematics for the SOM and reference carrier boards available for customers?
They do, yes. You can get in contact with our support team and request those schematics for your development.
Okay. What design software/tools is PHYTEC using for the schematic to 3D model process?
Good question. So yeah, we're doing most of our work using SolidWorks. There are some 3D capabilities for layout and Mentor graphics, but we found that we're able to get more precision and more flexibility with what we're doing with SolidWorks, and that's been very helpful for our review process.
All right. How many layers are on a typical SOM, and how many layers should a carrier board use with the SOM?
Good question. Yeah, it's kind of what I touched on a little bit ago. For a SOM, those are smaller, and so we'll typically use somewhere between 10 to 14 layers. And for a carrier board, our PHYTEC carrier boards, maybe 6 to 10 layers, more so like maybe 6 to 8. It really depends on what you're going for and what size that you hope to have. The smaller the size, the more layers you might need if you're routing a ton of different signals. If you only have a few interfaces that won't require as much routing, you can get away with less layers, which will reduce your cost, make manufacturing easier.
Okay, next question. And what's the most common issue you see during a layout review or design?
I'd probably say spacing around your sensitive signals, like your high speed and your differential, your clock signals. Oftentimes when you have these space limits, it's hard to give the appropriate space that the interface really calls for. And what I mean by that is you're routing a bunch of signals in parallel together, and if they're too close and if they're high speed, they can start to couple noise into the nearby signals. So I'd recommend paying attention to that and trying to give as much space as you can, and watch out for coupling and emissions in your design.
Okay. Well, it looks like that's the last question we have. So that concludes our live Q&A. We'll stay on for about another minute if anyone wants to ask anything else, and then we can follow up with those via email. So thank you so much for joining us today. Glad we were able to keep it short and sweet for everyone. Please fill out the survey you'll be prompted with to let us know what you thought, how we can improve for future webinars, and be on the lookout for a follow-up email that will include a recap as well as the slides from today's talk. And we'll see you at the next webinar.